Ever get that feeling, when you're looking up at the stars on a really clear night?
Yeah.
And you kind of get this pull, this like almost a nagging curiosity about what's out there beyond our little planet.
Totally.
That's what we're going to dive into today.
Yeah.
We're talking all about outer space.
Outer space.
And I've got a ton of info here.
Oh, yeah. It's fascinating.
I've been digging through this stuff.
Yeah.
And our mission today, basically, is to go beyond just the simple, the dictionary definition of what outer space is.
Okay.
And really, get into the weird and the cool and the kind of mind-bending things.
Yeah, the really fascinating stuff.
Like what makes the universe so incredible.
Absolutely. It's like we can look at the pictures, and those are amazing, but then there's this whole other level of understanding that comes when you dig deeper. So that's what we're going to do today.
Yeah, it's like space is cool just to look at.
Right.
But it's so much cooler when you understand it,
Absolutely. So think of this as your cosmic cheat sheet, kind of a shortcut to wrapping your head around not just what you see, but what space actually is.
Yeah, what it's made of.
Yeah, where does it start getting really spacey? When does Earth's atmosphere really give way to this whole other environment?
Right.
But the really fun part, I think, is diving into all those little details, even the parts that seem empty. They're actually packed with surprising things.
Oh, absolutely. And I think that's one of the biggest misconceptions that people have about space.
Totally.
We just think of it as this big empty void.
Right.
So let's start with the basics. What is outer space? Like in the most fundamental sense.
Okay, so the simple answer is it's everything out there beyond Earth's atmosphere.
Mm-hmm.
The stuff between the stars and the planets, the gaps in between, all the stuff we can see.
Okay, but is it really empty?
Well, it's the closest thing we know of to a perfect vacuum.
Okay.
Imagine sucking all the air out of a room.
Yeah.
Now do that on a cosmic scale. That's basically outer space. It's pretty mind-blowing. But even though it's a vacuum, it's not truly empty.
Right.
You've got mostly hydrogen and helium floating around, but not in the way we normally think of them.
Yeah.
They're in a state called plasma.
Okay.
Which means the atoms are so energized they've lost their electrons, so they're kind of zipping around on their own. And then, of course, you've got all sorts of electromagnetic radiation.
Like light?
Light, yep. Radio waves, X-rays, the whole spectrum's all out there moving through space. And then there are cosmic rays.
Cosmic rays, those sound intense.
They are. They're these super high-energy particles that travel through space at incredible speeds.
Where did it come from?
A lot of different sources. Some come from the sun, others from exploding stars, even from outside our galaxy.
Yeah.
And you can't forget about neutrinos. They're these tiny, almost ghost-like particles that can pass through almost anything.
Oh, wow.
And then, just to make things even more interesting, there are magnetic fields weaving through all of this, and even tiny specks of dust.
So even though it's a vacuum, it's not what most people would think of as empty.
Not at all. There's more going on out there than you might imagine.
And then there's this idea of the temperature of space.
Ah, yes, temperature.
Right. Because we think of space as being cold, but is that always the case?
Well, the Big Bang, that event that's thought to have kicked off the whole universe.
Yeah.
It left behind a kind of afterglow. It's called the cosmic microwave background radiation.
Oh, I've heard of that.
Yeah, and this radiation sets a sort of baseline temperature for space. It's incredibly cold, about 2.7 Kelvin,
Okay.
which translates to about negative 270 degrees Celsius or negative 455 Fahrenheit.
So even the emptiest parts of space have a temperature.
Exactly. It's like a faint warmth left over from the universe's birth.
Wow, that's crazy to think about. And you
Yeah.
mentioned plasma between galaxies, which is incredibly spread out, right?
Incredibly, it's mind-bogglingly dispersed.
And it makes up a good chunk of the universe's matter.
It does. This intergalactic plasma is thought to account for about half of all the ordinary matter in the universe.
So half of all the stuff is out there in this almost completely empty state.
Yeah, pretty much. Think about it. Half of everything we consider stuff, all the atoms that make up stars, planets, us, everything,
Yeah.
half of that is floating around in this incredibly spread out form between galaxies. And while the density might be incredibly low, like less than 1 atom per cubic meter, the temperature of these particles can be incredibly high, reaching millions of kelvins.
So it's like this incredibly diffuse material that's also super hot.
Exactly. It's a strange concept to wrap your head around, but it's true.
Yeah.
And it's just another example of how things can be very different in space than they are here on Earth.
Yeah, it's like a whole different set of rules. So we have these massive voids that are almost perfect vacuums, and then we have matter clumped together into stars and galaxies. But even within those structures, it's mostly empty space.
Absolutely. If you could take all the stuff out of an atom, you'd be left with almost nothing. Now imagine scaling that up to a star or an entire galaxy. They look solid and bright from a distance, but zoom in and it's mostly empty space at the atomic level.
It's almost like an optical illusion then. Like our brains tell us it's solid, but it's not.
Kind of, yeah. And it gets even more interesting when you consider that all this ordinary matter, the stuff we can see and interact with, makes up less than 5% of the total mass and energy in the observable universe.
Wait, so what's the rest of it?
That's the big mystery. The rest is made up of this stuff we call dark matter and dark energy.
Right, dark matter, dark energy. Everyone's heard of them, but nobody seems to know what they actually are.
It's true. We can't see them directly and we don't fully understand them, but we know they're there because of their effects on the things we can see. It's like we're exploring this vast cosmic ocean, and all the familiar islands, the stars, and galaxies are just tiny specks compared to these unseen currents and depths.
So the universe is even more mysterious than we thought.
It certainly is. There's so much we still don't know. It's
Yeah.
kind of exciting, right?
Totally. Okay, so we've talked about what's in space, however sparse, but where does space actually begin? Is there a clear line where Earth's atmosphere ends and outer space starts?
That's a tricky one. It's not like crossing a border between countries,
Right.
Earth's atmosphere doesn't just suddenly stop. It gradually thins out as you go higher and higher until eventually it becomes so thin, it's essentially the same as the vacuum of space.
So there's no hard boundary.
Not really, no.
Yeah.
But we do have this thing called the Kármán line, which is at an altitude of 100 kilometers or 62 miles.
The Kármán line, that sounds familiar.
Yeah, it's been adopted internationally as the official start of space, at least for things like treaties and aerospace records.
So it's more of a practical definition than a physical one?
Exactly. It's not like there's a giant sign up there saying, "Welcome to outer space."
Right.
But it's a useful convention. It's interesting to think that this line has such big implications, like who gets called an astronaut and how we decide who gets to do what up there.
Yeah, that makes sense. So below the Kármán line, we have something called near space, right?
Yep. Near space refers to the upper layers of Earth's atmosphere, specifically the stratosphere and mesosphere.
So it's kind of like a transition zone between the air we breathe and the vacuum of space.
Exactly. It's too high for conventional airplanes, but not quite space.
Okay, that makes sense. Now, thinking about all this, it makes me wonder about who gets to be in space. Is it like international waters, a free-for-all?
That's where the Outer Space Treaty comes in. It was signed back in 1967, and it's kind of like the Constitution for space.
Really?
Yeah. It lays out the basic rules for how countries are supposed to behave in space.
So what are some of the key principles?
Well, one of the most important is that outer space, including the moon and other celestial bodies, is free for all countries to explore and use.
Okay, that sounds fair.
Right. No one country gets to claim it as their own. And it also explicitly forbids any country from claiming sovereignty over any part of outer space.
So no planting flags and saying, this is mine.
Exactly. It's declared the province of all mankind.
I like that. It emphasizes that we're all in this together. But I've also heard concerns about, weapons in space. It seems like it would contradict the idea of peaceful exploration.
You're right to bring that up. It's a real concern. The Outer Space Treaty prohibits the placement of nuclear weapons and other weapons of mass destruction in orbit or on celestial bodies.
Okay.
But it doesn't ban all weapons. There have been tests of anti-satellite weapons by several countries.
Oh, wow. So it's not a perfect system.
Not yet, no. There are still a lot of challenges and discussions happening around how to ensure that space remains a peaceful environment for everyone.
It seems like there's always that tension, right, between wanting to explore and wanting to control.
Yeah, it's definitely a balancing act. But hopefully we can figure it out as we go along and keep the focus on cooperation and discovery.
Fingers crossed. Now, let's take a step back for a moment and look at how humans even came to understand space as this vast, mostly empty place. It must have been a pretty gradual realization, right?
It was, definitely. Back in the 17th century, after scientists like Galileo and Torricelli started proving the existence of a vacuum here on Earth.
Right.
The idea of a vacuum existing between Earth and the moon started to gain some traction.
That must have been a pretty radical idea at the time.
It was, yeah. It went against the prevailing view that space must be filled with something, like a mysterious substance called ether.
Right, I've heard of that. So how did we get from there to our current understanding?
Well, In the early 20th century, astronomers started measuring the distances to other galaxies.
And they realized just how vast everything really is.
Exactly. That was a huge shift in our understanding. We went from thinking that the Milky Way was the whole universe
Yeah.
to realizing that it's just one of billions of galaxies scattered across this incredibly immense cosmos.
And then on top of that, we actually started venturing out into space ourselves.
It's incredible, isn't it? From just looking up at the stars to actually going there.
It's mind-blowing. And it all happened so quickly, relatively speaking.
It did. We went from the first high-altitude balloon flights to Yuri Gagarin's orbit of Earth in just a few decades. And we've continued pushing the boundaries ever since. Though, sending humans into space is incredibly expensive.
It is.
Which is why most of our exploration beyond Earth orbit has been done with uncrewed spacecraft.
There are robot explorers.
Exactly. They've been to every planet in our solar system, and some have even ventured beyond.
That's amazing. And it's interesting to think about how even the word space has evolved over time. It wasn't always outer space, was it?
No, it wasn't. Actually, the use of the word space to refer to the region beyond Earth's sky goes back to the 17th century, when you find it in works like John Milton's Paradise Lost.
So space was the original term.
It was. And then in the 19th century, you start seeing phrases like outward space popping up.
Outward space.
Yeah. And it was around the mid-1800s that the term outer space, as we use it today, started gaining popularity, especially in astronomy.
So it was a gradual shift in language, reflecting our evolving understanding.
Exactly. And the interesting thing is that this shift was happening alongside the development of science fiction, which also played a role in popularizing terms like outer space.
So it was a kind of interplay between science and literature that shaped how we talk about space today.
Absolutely.
Yeah.
They were both influencing each other. And speaking of influential figures, Theodor von Karman, the guy behind the Kármán line, had his own specific definition of space.
I remember reading something about that. Wasn't it related to aerodynamics?
It was. He used the term free space to describe the altitudes where a spacecraft wouldn't experience significant atmospheric drag, the friction from air.
Okay.
But it was more than just an aerodynamic definition for him. It also tied into this idea of where a nation's airspace jurisdiction ends.
So it had legal implications as well.
Yeah, it was about defining the boundary between Earth's atmosphere, which is considered part of a nation's territory,
Right.
and outer space, which is free for everyone to use and explore.
And just to be clear, what's the difference between spaceborne and space-based? Because I hear those terms thrown around a lot.
Good question. Spaceborne generally refers to something that is carried into or exists in outer space, often by a spacecraft, like a spaceborne telescope or a spaceborne experiment.
Okay.
While space-based usually means something is located or operating in outer space, like a space-based satellite navigation system.
So spaceborne is about the object itself,
Exactly.
and space-based is about its location or function.
You got it. It's a subtle difference, but it can be important in certain contexts.
Thanks for clearing that up. Now let's zoom out to the biggest picture, the universe itself. We know it's vast beyond comprehension, but does it actually have an edge?
The age-old question. Honestly, we don't know. The size of the entire universe is one of the biggest unsolved mysteries in cosmology.
Really? We have no idea.
We have some ideas, some theories. Some suggest it might be infinite, stretching on forever in all directions. Others propose that it might be finite, but unbounded.
What does that even mean? Finite, but unbounded.
It's a mind-bending concept. Imagine a flat sheet of paper, but curved in on itself so that it forms a sphere.
Okay, I can kind of picture that.
So if you travel in one direction on this spherical sheet, you'll eventually end up back where you started.
Right.
But there's no edge to the sheet itself. That's kind of the idea behind a finite but unbounded universe.
Wow, that's trippy. So we might never know the true size of the universe.
It's possible. But what we do have a pretty good understanding of is the observable universe.
Okay, and that's just the part we can actually see, right?
Exactly. It's the portion of the cosmos from which light has had time to reach us since the Big Bang.
The Big Bang. So the universe had a beginning.
According to the prevailing theory, yes. The Big Bang theory suggests that the universe began about 13.8 billion years ago from an incredibly hot, dense state.
So it's been expanding ever since.
Yes, and one key point in that expansion was the recombination epoch, about 380,000 years after the Big Bang.
Recombination epoch, that sounds important. What happened then?
That's when the universe cooled down enough for protons and electrons to combine and form neutral hydrogen atoms.
Okay.
Before that, the universe was basically this hot, dense soup of charged particles, and light couldn't travel very far without being scattered.
So it was opaque, like a fog.
Yeah, exactly. But after recombination, the universe became transparent.
And light could finally travel freely.
Exactly. That's why we can see the cosmic microwave background radiation, that afterglow of the Big Bang.
So it's like a snapshot of the universe when it was just a baby.
Exactly. And it's one of the most important pieces of evidence we have for the Big Bang Theory.
Wow, so much happened in the first few 100,000 years.
It was a wild time, that's for sure. And then, over billions of years, gravity started pulling all that matter together, forming the first stars and galaxies.
And the voids between those structures became what we perceive as outer space.
Precisely. It's like gravity sculpted the universe, shaping it into the amazing tapestry we see today.
Okay, so gravity played a key role. And because light has a finite speed, does that mean there's a limit to how much of the universe we can see?
It does. We can only see as far as light has had time to travel to us in the 13.8 billion years since the Big Bang. So the further away we look, the further back in time we're seeing.
That's incredible. It's like we're looking at cosmic rational fossils.
It really is. And it means that there could be vast regions of the universe beyond what we can currently see.
Wow, so there might be entire galaxies out there that we haven't even glimpsed yet.
Exactly. The observable universe is just a tiny fraction of what might be out there.
Okay, so we have this incredible vastness. But what about the shape of the universe? How can something so big even have a shape?
When cosmologists talk about shape, they're referring to the overall geometry of space-time, the fabric of the universe itself.
Okay, I'm following.
Imagine a flat surface, like a tabletop. Parallel lines on that surface will stay parallel forever, right?
Right.
But on a curved surface, like a sphere, parallel lines eventually converge. So by measuring how light travels across vast distances, we can get clues about the overall curvature of the universe.
And what have those measurements shown?
Well, data from the cosmic microwave background radiation strongly suggests that the observable universe is incredibly close to being flat.
So it's not curved in on itself like a giant ball.
Not according to the best evidence we have right now. Now, this doesn't mean the universe is perfectly flat.
Okay.
Massive objects like stars and galaxies do warp space-time locally.
Right, gravity.
Exactly. But on the largest scales, it seems that the universe is incredibly close to being flat, which has really interesting implications for its fate.
So a flat universe, that's pretty mind-blowing. And you mentioned dark energy earlier. What role does that play in all of this?
Ah, yes, dark energy. One of the biggest mysteries in cosmology. You see, not only is the universe expanding, but that expansion is actually accelerating.
Really? So it's not slowing down as you might expect?
Nope, it's speeding up. And that's where dark energy comes in. We think dark energy is this mysterious force that's pushing everything apart, counteracting gravity.
So it's like an anti-gravity.
In a way, yes. And it seems to be an inherent property of space itself. The more space there is, the more dark energy there is, and the faster the expansion accelerates.
That's a scary thought. So the universe is just going to keep expanding forever.
It's looking that way, yeah. And eventually everything will be so spread out that the night sky will be completely dark, with no galaxies visible at all.
Wow. That's both amazing and kind of depressing.
It is. But it's also billions of years in the future, so we have some time to get used to the idea.
That's a relief. So we've talked about shape, expansion, dark energy. What about the actual density of matter in the universe? Is it as empty as it feels?
The best estimates suggest that the average energy density of the universe is equivalent to about 5.9 protons per cubic meter.
Okay.
And that includes everything: dark energy, dark matter, and ordinary matter, all the stuff we're familiar with. But here's the kicker. Atoms, the things that make up you and me and everything we see around us.
Yeah.
They only account for about 4.6% of that total density.
So less than 5% of the universe is made of the stuff we know.
Yep. That means there's roughly 1 proton per 4 cubic meters of space on average.
Wow, that's incredibly sparse. I guess that really emphasizes just how much of a near-perfect vacuum outer space is.
It does. It's by far the closest we've ever come to a perfect vacuum.
Okay, but how close to perfect are we talking?
Well, to give you an idea, the air we breathe has about 10 to the power of 25 molecules per cubic meter.
Okay.
And intergalactic space, which is about as empty as it gets, has only a few hydrogen atoms per cubic meter.
Right.
The difference is just astronomical.
Yeah, no kidding. And this near-perfect vacuum, it must have some pretty significant consequences, right?
Oh, absolutely. For one thing, it means there's almost no resistance to motion in space.
So things can just keep moving forever.
Pretty much, yeah. That's why planets can orbit stars for billions of years without slowing down. And it's also why light can travel such incredible distances through space without being scattered or absorbed.
Okay, that makes sense. But there must be some limitations, right?
Of course. The occasional dust grain or gas cloud can still block or scatter light, a phenomenon astronomers call extinction.
So even though space is mostly empty, there's still a bit of stuff out there to get in the way.
It's true. And astronomers have to account for that when they're observing distant objects.
That's fascinating. It's like even in the emptiest regions, there's still something to discover.
Exactly. Now, thinking about planets and moons, they manage to hold on to their atmospheres.
They do.
But where does the atmosphere end and the vacuum of space begin? It's not like there's a hard line, is it?
Right. Yeah.
It's more of a gradual fading. The density of the atmospheric gases just decreases exponentially as you move away from the planet, until it eventually becomes so thin that it's essentially the same as the surrounding space.
So it's more of a gradient than a wall.
Precisely. And for Earth, at that conventionally defined boundary of 100 kilometers, the Kármán line,
Yeah.
the atmospheric pressure is already a tiny fraction of what it is at sea level.
Wow. So it drops off pretty quickly.
It does. And above that altitude, the remaining gas is influenced more by things like solar radiation and the solar wind than by Earth's gravity.
So it's a complex interplay of forces that determines where the atmosphere ends and space begins.
It is.
Yeah.
And it's not the same for every planet. Each planet has its own unique atmospheric structure, depending on its size, composition, and distance from the sun.
That makes sense. So earlier we talked about that really cold baseline temperature of space, the one set by the cosmic microwave background radiation. But I've also heard about incredibly hot regions in space.
Right.
Like, how does temperature even work in a near-perfect vacuum? It seems like a contradiction.
It's a good question, and it highlights one of the common misconceptions about space. You see, when we talk about temperature here on Earth, we're usually talking about the temperature of the air around us, or the temperature of objects we touch.
Right, what we feel.
Exactly.
Yeah.
But in space, there's not much stuff to have a temperature in that sense.
Okay.
The radiation in space, like sunlight, can be incredibly hot. But if there aren't many particles around to absorb that energy,
Yeah.
it won't actually feel hot.
So it's more about the energy of the radiation than the temperature of the space itself.
Exactly. The temperature we measure in space is usually a measure of the average kinetic energy of the gas particles, which is how fast they're moving around.
Okay, so if there are very few particles,
Right.
the temperature can be very low, even if there's a lot of radiation present.
Exactly. It's like the difference between the heat from a fire and the temperature of the air in a room. The fire itself is incredibly hot, but if the room is large and there's not much air to heat up, the air will still feel relatively cool.
That's a good analogy. So what are some examples of this extreme variation in space temperature?
Well, the Boomerang Nebula is one of the coldest known places in the universe.
How cold are we talking?
It's been measured at about 1 Kelvin, which is just a fraction of a degree above absolute zero.
Wow, that's insanely cold. What about the other extreme?
On the other end of the spectrum, the sun's corona, which is its outer atmosphere, can reach temperatures of over 1,000,000 Kelvin.
Millions of degrees. That's mind-blowing. So the idea of a single temperature of space is pretty misleading.
It is. It really depends on what you're measuring and where you're measuring it.
Okay, that makes sense. Now, what about magnetic fields? We've talked about them a little bit, but they seem to be pretty important in space.
They are. Magnetic fields are everywhere in the universe.
Really?
Yeah. We've detected them around planets, stars, galaxies, even in the vast spaces between galaxies. They play a crucial role in many astrophysical processes.
So what do they do?
Well, for example, in star-forming regions, magnetic fields can help to channel gas and dust into denser clumps.
So they help stars to form.
Exactly. And in active galaxies, magnetic fields are thought to power those enormous jets of material that we see shooting out from the centers of these galaxies.
Wow, that's amazing. So even though we can't see them directly, magnetic fields are shaping the universe around us.
They absolutely are. They're like invisible scaffolding, influencing the structure and evolution of everything from stars to entire galaxies.
Now, let's bring it back down to Earth, or at least to human experience in space. What's it actually like for us out there?
Well, the most immediate challenge is the vacuum.
Right, no air to breathe.
Exactly. And without the protection of a pressurized spacesuit, the lack of atmospheric pressure would be fatal. Your blood would literally boil.
Oh, wow, that's gruesome.
It is. But even with a spacesuit, there are still plenty of dangers. Astronauts are constantly bombarded by radiation from the sun and from deep space.
And that can have some pretty serious health effects, right?
It can. Short-term exposure can cause things like fatigue, nausea, and a weakened immune system. And long-term exposure can increase the risk of cancer and other diseases.
So it's a really harsh environment. And I've heard some weird things about the smell of space.
Oh yeah, the smell of space.
Is that a real thing?
It is.
Huh.
Astronauts who've done spacewalks often report a distinct metallic, almost burnt smell clinging to their suits.
Really? Like what?
Some have compared it to welding fumes or burnt steak or even gunpowder. And there are a few theories about where the smell comes from.
Okay, what are they?
Well, one idea is that it's caused by the interaction of atomic oxygen with the materials of the spacesuit.
Atomic oxygen.
Yeah, it's a highly reactive form of oxygen that exists in the upper atmosphere. Another theory is that the smell is from dying stars.
Dying stars.
Yeah, some scientists believe that the death of stars releases polycyclic aromatic hydrocarbons, or PAHs,
Okay.
which have a distinct smoky, burnt smell. And these PAHs can be found throughout the universe.
So the smell of space might be the smell of dying stars.
It's possible. It's a pretty poetic thought, isn't it?
It is. So space is dangerous. It's got a weird smell, but it can also be surprisingly hospitable to some forms of life.
Oh, absolutely.
It's incredible what some organisms can survive.
It is. Certain types of lichen, plant seeds, and even some bacteria have been shown to withstand the extreme conditions of space.
Like the vacuum, the radiation.
And all of it, yeah. They can endure those conditions for surprisingly long periods of time.
That's amazing. So while space might be deadly for us humans,
Right.
life in general is pretty darn resilient.
It is. It finds a way. And this has led to some pretty interesting theories about how life might have spread throughout the universe.
Oh, like panspermia.
Exactly. The idea that life could travel between planets or even star systems, hitching a ride on asteroids or comets. So maybe we're all descended from alien microbes.
That's a wild thought. But for us humans, going out into space without a spacesuit is pretty much instant death, right? I remember learning about the Armstrong line.
It's the Armstrong line. It's named after Neil Armstrong, the first man to walk on the moon.
Okay.
And it's the altitude at which atmospheric pressure is so low that water boils at body temperature.
So your blood would boil.
Exactly. Above that altitude, which is about 19.14 kilometers, or around 63,000 feet, your bodily fluids would start to vaporize.
Wow, that's a pretty hard limit then.
It is. And even below that altitude, sudden exposure to very low pressure can be incredibly dangerous.
Like if your spaceship suddenly sprung a leak?
Right. Or if you were doing a spacewalk and your suit was damaged. The rapid decompression could cause all sorts of problems. Your lungs could rupture, your eardrums could burst, you could get the bends.
So it's not just the vacuum itself, but the sudden change in pressure that's dangerous.
Exactly. It's a really harsh environment. And it shows just how adapted we are to Earth's atmosphere.
Absolutely. And what about the effects of weightlessness? We've all seen those cool videos of astronauts floating around, but I imagine there are some downsides to that too.
Oh, there are. Prolonged exposure to weightlessness, or microgravity as it's called, can have a significant impact on the human body.
Really? Like what?
Well, initially, many astronauts experience space motion sickness.
Like car sickness, but in space.
Kind of, yeah. It's caused by the conflicting signals your brain receives from your inner ear and your eyes,
Right.
leading to symptoms like nausea, vomiting, and disorientation. And in the longer term, the lack of gravity leads to muscle and bone loss.
Because your body doesn't have to work.